Welcome to Study Loop.
Okay, so we have three long parallel wires that each have current I, and they're each separated by a distance d. And we want to find the force per unit length on each wire. So here's our equation in general for the force per unit length on a wire from another current. So first thing to notice is that the magnitude of all of these wires is the same. So for all of these cases, we can replace both I1 and I2 with just I, and so this is going to give us I squared up here. So this is going to be the general formula that we need to use. So let's look at the top wire. So for the top wire, again, we're going to need this formula, and what we're just going to want to do is add up the contribution from each of these wires individually. So let's first think about this first top wire. We know that that the distance between this top wire and the middle wire. So the middle wire is going to contribute a field here that's going to cause a force. And again, the magnitude is just I, and it's separated by a distance d here. Now what we're going to want to do is add the force coming from this bottom wire. And now the bottom wire is a distance 2d away. So this d, it now becomes 2d, and I'm just going to absorb. Actually, yeah, we'll just leave it like this. And notice, though, that the current from this wire is traveling in the opposite direction as the current from this direction. So let's just arbitrarily say that we're going to call the currents going to the left positive and currents going to the right negative. So I'm going to make this whole thing negative because we now have a negative current, negative contribution down here. So what we can do is condense this a little bit because we have a lot of constants. So we have mu naught times I squared, and then we also have a factor of 2 pi in the denominator. And then we just have 1 over d from this first term minus 1 over 2d from this second term. So this is going to be the expression for this. And this, when we simplify it, this is basically saying we have, we can just simplify this fraction here and combine the results with this. And when we simplify this fraction, we're just going to get mu naught times I squared over, we'll have 4 times pi times d. Now let's think about the direction that the force is going to be in. Now remember that two wires that are carrying current in the same direction are going to attract, and wires that carry current in opposite directions are going to repel. And thinking about these two bottom wires, the force on the top wire is going to mostly come from the middle one. So the middle one is closer to the top. So the force from the middle one is going to dominate. And so if we think about these two currents that are in opposite directions, that means they're going to repel. So the net force here is going to be upwards on this top wire here. Now let's think about the middle wire. We're going to have the same, we're going to start out the same way. We have F per L. Let's think about the force coming from the top wire. So that's going to just be expressed here because we have a distance d. But we, well, this is going to give us a distance d. And let's think about the direction of the force. Since these are both in opposite directions, they're going to repel. So this middle wire is going to be pushed down by this top wire. Now, if we think about the force per unit length on coming from the bottom wire, we have the same magnitude because it's separated by the same distance. And again, these two currents are in opposite direction. So these two currents are going to repel as well. So the bottom wire is going to exert a force on the middle wire that's upwards. So we have a force exerted downwards from the top wire and a force exerted upwards from the bottom wire. And we know that they have the same magnitude because they're both separated by the same distance and have the same current. So that means that it's actually just going to totally cancel out because they're in opposite directions. And this net force is going to just be 0. Now let's think about the bottom wire here. We could explicitly go through and do the same calculation, but hopefully you can see that because of symmetry, we have a middle wire that is separated by a distance d here, and we have a farther wire, which is the top wire here in an opposite direction. That's going to contribute the same magnitude as this over here, separated by distance 2d. For the magnitude of the magnetic field, we're going to get the same result as in this top wire up here. So we don't really need to do any new calculations because we can just see that since this problem is symmetric, it's going to give us the same result. And to find the direction, remember this middle wire is closer, so the force from this middle wire is going to dominate. And these currents are in opposite directions, so this bottom wire will be repelled by the middle wire, which means it will be pushed downwards. So the force is going to be down.